Alright, so here we go. Here's this answer key for you guys. And please, 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 please heed my warning like what I said before on these. Guys, this is also on the notes and stuff we went over before we had break. So look at that stuff. That stuff still is applying on what we're discussing and talking about. And always remember, once you learn it, don't forget it, and all is fair game. So let's work this. And on these electron dot diagrams, I'm going to need a big table. Let's see here. On these, remember how these electrons fill in. Pretty much this is like the simplest thing ever. So there's X just as a filler. First electron, second electron, third electron, fourth electron because of Hund's rule, fifth electron, Hund's rule, 6, 7, 8. That's the order we're going to fill these in, and that's how we're going to flow in. So in this is pretty much find out how many valence electrons they have. So sodium comes from the first column, 1 valence electron. So right there, we're done. Sulfur has 6 because it's in the 16th column. So 1, 2, 3, 4, 5, 6. Now we'll be looking for that, okay? Fluorine has 7. It's in the 17th column. 1, 2, 3, 4, 5, 6, 7. Boron, 13th column, so 3, 1, 2, 3. Carbon has 4 because it's in the 14th column, so 1, 2, 3, 4. Tellurium is in the 16th column, atomic number 52. 1, 2, 3, 4, 5, 6. Then we have germanium. Germanium is in the 14th column, so that's 4. So 1, 2, 3, 4. And we're done with those electron dot diagrams. Those are not too bad. It's just these Lewis structures I want to make sure you guys are feeling good with. So I'm going to work through these, and I'm going to do everything visually except for dividing out those charges and everything at the end. So let's get started. First one we got is CH4, which is methane. Step 1, you will find the center atom. The center atom is always the one with the lowest electronegativity. In this, except for hydrogen, it can never be hydrogen. So in this case, the only other option I have is carbon. Then in step 2, we draw the skeleton. I bond 4 hydrogens to it. Give everything a full octet where required. Remember, hydrogen is one of those rule breakers, so hydrogen only receives 1 bond. So none of these get a full octet, and carbon has a full octet because of the bonds around it. Now in this, I need to check and make sure I'm showing the proper number of electrons. And we do this in terms of valence electrons. So I have carbon and hydrogen. I have 4 hydrogens and 1 carbon. Per carbon, I have 4 valence electrons because it's in the 14th column. Per hydrogen, I have 1 valence electron. 1 valence electron per hydrogen, and I have 4 of them, so 4 plus 4 is 8. So I have to show 8 electrons. Count and make sure we're showing the proper number. These bonds count as 2. Always remember that. So 2, 4, 6, 8. Now that we're done with that, we're showing the proper number. We don't have to add any double or triple bonds because we're showing the proper number, but now we just need to check our charges. So remember, whenever we're doing that, it's in terms of the valence electrons they normally have. All these hydrogens are the same.
Bill Taylor, come to the office. Brady Smith, come to the office.
Hydrogen normally has 1 valence electron, so we will subtract from it however many it is now showing, and we split those bonds in half. We do not do it physically, we do it mentally. Alright? So we split them in half, the electrons go to the end, so 1. Gives me 0. It's neutral, that's good. Carbon also should show up neutral here because there is no overall charge. Carbon normally has 4, and if we check, 1, 2, 3, 4, it has 4 as well. 0. There is our complete Lewis structure for methane. Okay? Not too bad. We'll step down here to silicon tetrafluoride. So in this case, we will find the center atoms along with the lowest electronegativity. So in this case, it's going to be silicon. That's the center atom. We're going to draw the skeleton. So within this, we will find there's a skeleton. We need to give a full octet to everything. Silicon's good with those 4 bonds, but we're going to need a full octet for the fluorine. And I probably should have showed you where this came from in case you don't know. So the reason I did that is because it wants 8 electrons. All those fluorines are the same. They all want 8 electrons, and in this case, they all have a bond, which means they have 2 electrons. Since they have these 2 electrons, then what they're looking for in here is they need 6 to get to 8. And we do this in terms of lone pairs. So I divide that by 2. It wants 8. It already has 2. That's from the bond. Okay, so the 2 is from single bond. We get 6. Need 6 electrons. We do it in terms of lone pairs. So pairs like tennis shoes. So divide by 2 is 3. So we need 3 lone pairs. Everyone gets 3 lone pairs. Now we calculate out how many we're supposed to show. So I have silicon and fluorine. I have 1 silicon, 4 fluorine. In this case, silicon is in the 14th column, which means it has 4 valence electrons. 1 times 4 is 4. Hold on. This video on processing started playing for whatever reason. Alright, from here, fluorine is in the 17th column, so that's 7 valence electrons. 4 times 7 is 28. Add that together, gives me 32. I'm supposed to show 32 electrons in this case. I'm showing 1, 2, 3, 4, 5, 6, 7, 8, because the bonds count. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. I'm showing 32 electrons, so I don't need to worry about adding double or triple bonds. I just need to check charges now. All the fluorines are the same. So fluorine normally has 7 valence electrons. Split those bonds in that half, and what we'll find is that we're showing 7 electrons. That's neutral. Now silicon needs to be neutral as well because there is no overall charge. And whenever we do this, what we find is silicon normally has 4. Split those bonds in half. 1, 2, 3, 4. It also is showing 4, so it's neutral. So there is my proper Lewis structure for silicon tetrafluoride. Okay? Hopefully you're doing good with these. I really pray so. I'm like getting bored to death with constantly running through them. Now, in this I'm going to tell you that this carbon dioxide, if you remember it from class, it is going to require double or triple bonds. So this is what I'm going to do. I'm going to use my black pen as kind of an eraser. So whatever I mark out with my black pen is erasing kind of the idea of it, so that you can get the idea. I still want to do this in pen because it gives me the ability to do it in multiple colors so that you can tell the difference between these. But I want to make sure that you follow and understand that. So in this case, we're going to start with carbon dioxide. So in this case, find the center atom. Hopefully you're saying right now the center atom is carbon. Then you're looking saying step 2, draw the skeleton. So we're going to bond these oxygens with it. We're going to give the full octets where needed. So oxygen wants 8. It's not a rule breaker. It has 2 electrons from that bond, which means so we have 8, have 2 from the bond. I need 6 electrons, and we do it in terms of pairs. So whenever we're doing this in terms of those pairs, what are we going to look at? We're going to divide it by 2 to give the pairs. So I need 3 lone pairs. 1, 2, 3. 3 lone pairs. And same thing with this oxygen over here because it's the same. I really believe you guys are catching on with that. Now this carbon's different. Carbon wants 8. And it has 4 because it has 2 bonds to it. Okay, so it wants 4 now. Divide that by 2, gives me 2. It needs 2 lone pairs. 1, 2. There's the pairs. Please notice at this point, I've done nothing. I've not looked at the periodic table with this yet to figure out how many electrons I'm supposed to show or anything. I'm now moving on to step 3 to calculating the proper number of electrons I have to show. So in this case, we're going to look at carbon, we're going to look at oxygen. I have 1 carbon and 2 oxygens. 1 because there's not a number there which represents, it's kind of like in math, okay, there has to be a 1 there or we wouldn't put the C. And then there's a 2 next to the oxygen which gives me the 2 oxygens. Now in this, what we're going to say and look at doing is the valence electrons off the periodic table. Now the periodic table comes into play. So how many valence electrons for my carbon? It's in the 14th column, so that means it has 4 valence electrons. Oxygen is in the 16th column, so that means it has 6 valence electrons. If you do not understand where this is coming from, please go back to the original video a long time ago whenever I did this and I talked about the valence electrons on these things. When we talked about the valence electrons, said D block doesn't matter, F block doesn't matter, they don't fall in with suit. But the first column has 1 valence electron, second column has 2 valence electrons, 13th column has 3. Okay? Another way of thinking of it is just remove that first number there and it'll give you the valence electrons. Because 14th column is 4, 15th column is 5, 16th column is 7, 17th column is 7, and 18th column is 8. So 1, 2, 3, 4, 5, 6, 7, 8. So in this, I get 1 times 4 is 4, 2 times 6 is 12, which gives me 16. I'm supposed to show 16 electrons. In this case, count it up. You need to be able to count this properly. Okay? Remember to count these bonds or you're going to mess up here. Because I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 electrons. I'm showing too many electrons. So to fix this, we have to add double and triple bonds where needed. Okay? And remember, keep this as symmetrical as possible. So I'm going to start on the left because we read left to right. So there's a double bond. Now as soon as I did that, think back to what I said before. You've got to remove these off. Alright? These have to get removed off. And this is as to why they must be removed. Look at this oxygen. It is now showing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. And the same thing for the carbon. Because 1, 2, this bonds to it. 3, 4, 5, 6, 7, 8, 9, 10. That can happen. So, like I said, I'm going to use my black pen as an eraser. We need to take off some lone pairs. So I'm going to take these 2 off. I'm going to take these 2 off. Now count up and see how many we're showing overall now. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 electrons. I'm still showing too many. So in this case, we're going to add another double bond. Now you can add a triple bond here, but you're not going to be right if you put it here on the left and leave a single bond over here. And the reason as to that is it's going to put a charge in here, and this thing wants as much symmetry as possible and wants as little charge as possible to help with handling that issue. They don't want charge. They want stability. That charge is not giving great stability. So they will separate these electrons as much as possible. In this case, looking at here, we need to take off a lone pair here and a lone pair there. Remember, my trick to that is wherever I put the dash, the two atoms it touched, I removed the electrons from it. Those lone pairs off from it, okay? Now what I'm going to do is, because that looks horrible as a properly drawn Lewis structure, I'm going to draw it properly over here without the black pen ink being an eraser, alright? And that is what the Lewis structure should look like for carbon dioxide. Okay? Remember, if you have questions, come see me. Okay? I'm going to pick up a pace a little bit, so you should be seeing where he's coming from. You do need to split these in half and check these charges, but there's not any charges there, so I'm going to leave it as it says. I hope that's cool with everybody. Not, sorry. Barium trichloride, boron, not barium. Boron I know why I'm messing up there. It's it's boron trichloride, that's what it is, boron trichloride. It doesn't roll off the tongue very well. Find the center atom. Center atom's going to be boron, lowest electronegative. Draw the skeleton. Give everything a full octet where required. So in this, these chlorines, they have 2 electrons because of these bonds, so they need 6 electrons, which transfers into 3 lone pairs. 1, 2, 3. Same thing for these other ones. Now there is a trick here, and hopefully you caught the trick. I'm finished. Do not put a lone pair on boron. This is why. Remember, boron is the second rule breaker for the octet rule. It only has 3 electrons to share and bond with. Therefore, it will only form 3 bonds. It will only take 3 bonds. It will not take a full octet. Okay? So let's look. Boron, chlorine. Boron has 3 valence electrons in 13th column. Chlorine has 7 valence electrons. It's in 17th column. I have 1 boron. I have 3 chlorines. So that gives me 3, 21. Add that together. So I should show 24 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I'm showing 24. I need to check and see if there's any charges. If there are, I have got to represent those charges. I have no other choice. So split the bonds in half. Looking at it, the chlorines normally have 7, and they're showing 1, 2, 3, 4, 5, 6, 7, because we split those bonds in half. But remember, I'm not doing it physically, so I don't have to redraw like I had to up here. You don't want to have to redraw. Save your time on this quiz. So that's 0. So the boron should be neutral as well. 3 minus 1, 2, 3. It's going to be 0. So this right here is the properly drawn Lewis structure for boron trichloride. Okay? Now, from here, we go into this guy, and this is the really cool one. This actually is the most stable bond on the planet. So in this case, we're going to find the center atom. A lot of y'all are probably asking, Mr. Hall, what is the center atom? We only have 2. How can we have a center? Well, it's nitrogen. Because either way you look at it, it's going to be nitrogen bonded to nitrogen. And again, I'm going to have to use my black ink pen as an eraser on this. and then I'll redraw it. So, draw a skeleton, give a full octet. I believe you guys are getting this by now. So you guys should start with that image right there of nitrogen. And then from here we're going to break it out. So we got to calculate how many we're supposed to show. So nitrogen, I have 2 nitrogens, and nitrogen is in the 15th column, so it has 5 valence electrons, so I'm supposed to show 10 electrons. Let's count it up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Snap! We're showing 4 too many, sorry. So let's add a double bond. Remember the rule. Add that double bond, we're going to remove the lone pairs between the 2 that it was grouped with. So we're going to remove here, remove here. Let's count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm still showing 2 too many. So let's add a triple bond in here. So we'll remove this lone pair and that lone pair. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now I'm showing the proper number. Let's check charge. Nitrogen normally has 5. 1, 2, 3, 4, 5. It's showing 5. It's neutral, which matches up with the charge, so that's good. So to redraw it, there we go. That's the properly drawn Lewis structure of nitrogen. Okay. Now, hopefully you got that front page really easy. We're going to move on to this second page. Okay. Just so you know, I'm probably going to make some of y'all mad with that one sheet that I gave y'all today. I'm probably not going to be able to make that in an answer key today. I'm so sorry for that. You can come to me in the morning and ask all the questions you would like those. So let's roll on this. I'll roll a little quicker to see how many of those we can get involved here. So hydrogen cyanide. So in this case, find the center atom. Center atom's lowest electronegative except for hydrogen, so it's got to be carbon. Draw a skeleton. Full octet. Like before, I'm going to use my black ink pen. Do not give hydrogen any lone pairs whatsoever. Remember, hydrogen is a rule breaker and it will only form 1 bond. Please remember that. Alright, from here we're going to calculate up how many of these we should be showing. So, hydrogen, carbon, and nitrogen. I have 1 of each of them. Then, I have 1 valence electron per hydrogen, 4 valence electrons per carbon, and 5 valence electrons per nitrogen. 1 times 4 is 1, 1 times 4 is 4, 1 times 5 is 5. Add these all together, gives me 10 electrons. I'm going to show 10 electrons. Let's count it up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Snap, we're showing too many again. So we got to do what we got to do. Let's add a double bond. There's only one place we can add things. It's on this right. Why? Hydrogen only forms 1 bond. So in this, we got to get rid of some lone pairs. Let's count it up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Still showing too many. Take these out because I'm going to add this triple bond right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now I get 10. There's that. Check for charge. Hydrogen should have 1. It has 1. No charge. Carbon should have 4. It has 4. 1, 2, 3, 4. No charge. Nitrogen should have 5. 1, 2, 3, 4, 5. It has 5. So we're good. Let's just redraw it. There is your properly drawn Lewis structure for hydrogen cyanide. Now, moving on to this next one. Ozone. So, draw the center atom. They're all the same, so they're all just going to be joined together like that. Give everything a full octet. Hopefully you can see that these on the outside need 3 lone pairs. And I am moving quicker. This is an answer key. This is not, at this point, you should not be looking and saying, snap, I don't know what I'm doing. I need to learn this. I'm watching this video. You should be watching the other ones where I went slower, okay? So give everything a full octet. This middle one just needs 2 lone pairs from here. Oxygen, we have 3 of them. There's 6 valence electrons per oxygen. That's 18 electrons we should show. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I'm showing 20. That's 2 too many. I'm going to add a double bond there. Take off that lone pair. Let's take off that lone pair. Let's check it out now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I'm showing the proper number. But in this, I got to notice something. First off, I got a resonance structure. This could have went over here, so I'll have to represent that in the final answer. Not only that, but we also have an issue. We need to look at the charges here. Oxygen should have 6. On this oxygen, 1, 2, 3, 4, 5, 6. So it's good. But look at this oxygen. Oxygen should have 6. 1, 2, 3, 4, 5. Well, 6 minus 5 is plus 1. So this right here, that oxygen has a positive charge. Now look over here at this one. This oxygen over here should have 6, but it has 1, 2, 3, 4, 5, 6, 7. 6 minus 7 is negative 1. This has a negative charge. You have to represent these charges as well. So let's redraw this out. We're going to have to show resonance. Have to show the charges within these. That's the negative one, there's the positive one, and there is my answer. There is the properly drawn Lewis structure. Alright, time out a second. I got some distilled water being made here in the back, and I got to turn it off before we got an issue. Alright, let's come back to it. Ammonium! Now life gets interesting. Now it becomes obvious to you that you should have charges in these. This one didn't sell the charge. These should, because they have charges on them. These should look very familiar to you. These are your polyatomics. So let's look at working these out now. Remember, black pen is used for eraser. Moving forward, let's go red. So in this center atom has to be nitrogen. Draw the skeleton. Full octet where required. None of them are requiring more than what they already have. Nitrogen has the full octet. These hydrogens are at peace the way they are. So let's remember in this how we deal with this. Nitrogen, there's 1 of them. There's 4 hydrogens. There's 5 electrons, valence electrons per nitrogen, and 1 valence electron per hydrogen. Please remember where I'm getting that from. I'm getting that off the periodic table. So 5, 4 gives me 9. Well, that's weird. Oh wait, I have this charge.
Also, Bob, come to the office.
You got to take that charge into account. It's a positive, which means you have lost a negative charge. So we've lost an electron. So we subtract 1 to give us 8. We're supposed to show 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Just from those bonds. So we're good, right? We're done. If you stop here, you are wrong. Because look, how many valence electrons does hydrogen normally have? 1. How many does it all these 4 have? 1 apiece. So that's 0. That's cool. But we have this positive charge. We have to have a positive charge in this molecule somewhere. But look at nitrogen. Nitrogen normally has 5. 1, 2, 3, 4. Oh, 5 minus 4 equals plus 1. So that nitrogen has a positive charge, and you have got to represent that. Okay? On this next one, carbonate, I'm going to need all the room I can have for it. So on this, and I will say that. Alright, so let's look at this. Carbonate. Center atom, carbon. Charles skeleton, full octet. Calculate the number of electrons for this. For carbon, we have one of them. 1 times 4 is 4. For oxygen, we have 3 of them. 3 times 6. 6 less electrons per oxygen is 18. It's 22. Add 2 to that because of that negative charge there. We added 2 electrons to it, so 24 electrons is what we should show. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. I'm showing 2 too many. How do we fix it? Booyah. Double bond. Take off these lone pair here. Remember, don't stop there. We drew this dash between this oxygen and this carbon. Take that off as well. Okay, so now we're showing the proper number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. We're showing us 24, but now keep in mind, there's that negative 2 charge. There's got to be some negatives in here somewhere. And hopefully it jumps off the page sheet. It's going to be these 2 oxygens out there on the outside. You should end up with a negative here and a negative there. So in this, you look this up, they're supposed to have 6, they're showing 7, 6 minus 7. That's what gives you the charge. So in this, I have to represent, I'm going to draw a little wall here. Resonance, because 3 different spots this could have went. So here's the first one. The resonance of it. Double bond there, let's put a double bond here, let's draw more resonance. Now we're going to fill them in. Negative charges. It's probably like the most boring video in the world to watch. Looks good. So here is my answer. And you must have all 3 of these drawn in there. If you don't have all 3, then you are wrong. Okay. Shoot. I got 10 minutes. Yeah, I definitely can get that second one in. Let's try and get these in though. Alright, so I held off here. Sulfate. Okay. So you should jump right off the page and go sulfur in the center, raw skeleton. Really full octet. In this case, you can look and say sulfur and oxygen in the same column, so I'm going to look and say it's 6 times 5, which gives me 30. and I have a -2. So I add 2 electrons to that. It's 32 electrons. Count it up. I know it's hard to see, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. But hold on. Remember when I tricked you guys in class with phosphate? This right here also is the same thing. If you look and you do this that way, all these oxygens are going to have negative charges on them. And this sulfur is going to have a positive charge to it. But we don't want that. That's the last thing we need. That's the last thing we want. That's the last thing we're desiring. So in this, I'm going to tell you, there's a way, since this is sulfur, it breaks the octet rule. It'll form 6 bonds. We need to break this out and apart. Okay, so we can put 2 double bonds in here to fix this, to get rid of these charges. Because whenever we do this, look, add a double bond there, add a double bond there. I've added 4 electrons. I have to remove lone pairs off here and here off these oxygens. So I've removed 2 lone pairs, which is me removing 4 of those. Whenever I do that, I don't have to remove anything off sulfur, so I've took away 4, but I've added 4 back. Now look at the charges. Oxygen should have 6. These 2 oxygens showing 7. So there's a negative, there's a negative. These oxygens are showing 6, so we're good. Sulfur should show 6. 1, 2, 3, 4, 5, 6. So it's good. Only thing is I got to show resonance. These 2 double bonds could have shifted over here. Okay? Build a wall. Oxygen, sulfur. Double bond up to oxygen. Double bond down to oxygen. Resonance of that. Oxygen. Sulfur. Oh, that's it. We got to flip this now. Then we're going to throw in these lone pairs in here. There's the 2 negative charges there. Lone pairs. Charges, everything's got full octet, sulfur rule breaker, so it doesn't matter on that one, and we're set. There is sulfur. It is a trick, okay? So watch yourself there. Alright? Guys, I only got 6 minutes left on this, so I'm just going to like toss down the answer for these last 2 so that you can see it, so that you can compare. Okay, so phosphate and perchlorate. On phosphate, you guys should be good. We did that one in class, but in case you're not, I want to make sure this is here for you. Alright, so answer-wise, remember, it's just answer-wise. I'm not going to really work through it. We have oxygen. There's a whole bunch of resonance. I'm going to put the double bond there first. Double bond's there. Negative. 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 That's right, X. Yeah. The resonance of it. Where I'm working this fast, if I made a mistake, refer back to the one we worked in class. Alright. And we'll go clockwise with the double bond. Let's do it that way. Negative. Negative. There's no pairs in. Negative. should have a bond now. So it's a good thing I use different color ink. Those are gonna run together. I was getting nervous when I do a big one like this, and I'm just rolling through it like this. And the last one. Negative, negative, negative. 1, 2, 3, 4. Okay, and I'll box it just so that nobody freaks out on me. That is a horrible box, but you get the point. It's in there. And chlorate, I'll actually have to work it out really quick. No, I'll spit on chlorate. Perchlorate, sorry. Everything's got a full octet. That's good. Man, this y'all up. No, we're good. We're good. Okay, chlorine should have 7. Oxygen, 6 times 4 is 24. And 1 from there, so that makes that 8. 32. That should 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 27, 28, 29, 30, 31, 32. So we're good there. And this is as to why. That'll have a negative charge, that had a negative charge, that'll have a negative charge, and that had a negative charge. But that looks horrible. How can we have that and we have a negative 1? Because this is 3 plus. So I'm going to draw it over here just so you can see it better. Negative, 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 and negative. There is your answer. Okay? So there's that one answered out, guys. As you just heard, the bell just rung on me. My physics class is getting ready to come in here. So I'm going to stop this, get this video editing and rendering so I can get it to you guys so you can use it for studying tonight. Remember, if you have a question on any of these, come and ask me, okay? Especially on these guys. Alright, I'll be here in the morning at 7:05. Feel free to come in and see me. And 5th period, you can always come in during lunch, which I'm sure a bunch of you will tomorrow. And here's this sheet that I gave you guys that I'm sorry I'm not going to be able to. Okay, I literally made this sheet today and I'm just not going to be able to get an answer key done for it today. I'm deeply sorry. But here's this one. If you can do these, including this back, and get all of this, guys, I feel comfortable in saying you'll do fine with anything I'm going to throw at you. If you can do that back sheet of the first one I gave you, you should be able to do these no problem whatsoever. I believe in you. If you got any questions, just message me. Two.